Welcome back, everyone, to the second part of our workshop. In this part, we have the winners of the 3D Building Model Reconstruction Challenge. So we have two presentations, and then we will continue with with our two keynotes. First, we have the second place presentation by Miguel Vega. From the Technical University of Munich. Miguel is working with Professor Andre Bormann, who is the chair of computational modeling and simulation. Miguel, the floor is yours, and you should be able to share your screen.
Thank you, Yelda. I just want to share my screen. Can you see it now?
Yep.
Okay, today I have the pleasure to introduce you Point Waiver, the method we developed for the 3D reconstruction challenge. This was a result of the collaborative effort of the Digital Twin Group. And in our method, we start basically with a raw point cloud, and we predict labels in this point cloud, detect 2D walls in 2D, and then detect doors, windows, and finally perform the 3D reconstruction. And so to perform the semantic segmentation, what we did is that we took the raw point cloud without semantics. We used the 3D models and aligned them together with the point cloud and perform an automatic semantic annotation step with a threshold of 10 centimeters. In this way, we could automatically segment the point cloud into different categories: walls, ceiling, door, floors, doors, windows, columns, beams, and clutter. That is in red here. Subsequently, we train KPConf with a training dataset, and after training, we could use this network to perform inference in a test dataset and obtain automatically segmented point clouds. So when we just isolate the predicted walls from the point cloud and we project them in 2D in the XY plane, we notice that there is effectively quite large difference. Instead of projecting all the points and only projecting the predicted walls, we have clean rooms which we can work with for the posterior steps. Next step was point cloud alignment, in which we project the predicted walls in a 2D image. Then we detect straight edges with a probabilistic Hoff transform with a precision of 0.1 degrees. And we use k-means to extract the angle of rotation, which then align the point cloud with the X and Y axis. Once the point cloud is aligned, we use an image processing step to separate the wall instances that are aligned with the X and Y axis. To do so, we first perform a dilation operation with a rectangular kernel. And with this step, we basically join all the walls in a singular blobs. And we also then perform a dilation operation with a custom kernel. In this case, we perform with a horizontal and a vertical kernel so that we can isolate the horizontal and vertical aligned walls, as you can see here. And then we can extract easily the middle points of horizontal and vertical walls and work with them for the next steps. What we did next was to merge and connect lines. This step was necessary because some walls were occluded during the scan acquisition, and also because the prediction of KPConf were not always very accurate. So to do so, we extend the bounding boxes of lines. We check if the bounding box is polite, and if the lines are almost parallel, and if they're close to each other, they are merged into one single line. For example, here this blue and these red lines are merged in one lines. And to do the connection, we do also a collision check in the bounding boxes. And if the lines are not parallel, we calculate the intersection point of the two lines and then extend the lines, so creating these resulting lines. Next, we detect doors and windows. In this step, what we do is we isolate one wall instance from the original point cloud. Here you can see the vertical view of the single one wall instance. And then we get the negative void space of this wall point cloud, that is basically the holes in the point cloud. Then we cluster these negative voids in different groups, and we remove outliers in each cluster. Possibly we find fit rectangles so that we can find doors and windows in the point cloud. Finally, we did the 3D modeling. We try to use XBIM toolkit for this task, but as you can see here, while working with the middle point of the walls, there are some not well modeled joints in the corners and in the intersection of the walls. For this and other reasons, we opted to use Revit, in which the joints are automatically solved. And in Revit, we are also able to add custom family types of doors and windows, and automatically export the model in IFC and DXF format. Additionally, we could also perform some verification in the Revit API regarding the orientation of, for example, the doors and windows that we want to insert. That is the same, have the same orientation of the hosting wall, and the center point of the element is inside of the wall. So, for example, in this case, this door is not created because it's outside of the wall. So finally, it's a summary. We have the original point cloud. We created walls with the trained KBConf, and we align the point cloud with the X and Y axis. We extract the Manhattan walls with an image processing step. Then we get better walls after line merging and connecting. And after door detection, door and window detection, we create 3D models that are exported into IFC, DXF, and possibly we can create an OBJ from the IFC model. Finally, I would like to thank NVIDIA for supporting this research and providing the necessary hardware. And here are some of our references. Thank you all for your attention, and I'm happy to answer any questions.
Great. Thanks for the great presentation, Miguel, and congratulations again. I see one question. Was your 3D modeling with Revit API fully automatic?
Yes. Well, in terms of if we have the input and the output, yes, it was fully automated. I mean, we get the input coordinates, start and end point of the walls and doors and windows, and we automatically obtain the IFC and the DXF files from the Revit API.
Great, thank you. I don't see any other questions. And yeah, for the sake of time, maybe we move to the next presentation. Thank you very much, Miguel. And if you can stay on a little more, and if you can just type in, I think there's another question coming in. So thank you.
Thanks to you.
Our next presentation is the winner of the 3D modeling challenge, Liu Yang and Yi-Chun Lin from Purdue University. Great, the floor is yours.
All right, hello everyone. Please allow me to stay on video connections as to keep the smooth of the network as I'm using a Wi-Fi. So yeah, good afternoon everyone. I'm Liu Yang, a PhD student from Civil Engineering, Purdue University. My teammate Jiao Lin will partner with me in this presentation. Before we start, we'd like to give our thanks to the organizers for offering this great workshop and data sets, as well as giving us the opportunity to participate and present our work on this webinar. Also, we would like to thank Professor Habib and Professor Kai for advising us in this challenge. So our approach is called semantic segmentation of point clouds using super point graphs with augmented training data sets. This presentation will consist of 6 sections, starting with introduction. So in one word, building information modeling has been widely used nowadays as it provides 3D models with rich information of objects. Within the scope of using point clouds to generate as-built BIM models, there are generally 3 steps, which are point cloud acquisition, semantic segmentation with point clouds, and 3D model reconstruction. Among those 3 steps, with our experience in the construction industry, we reckon that the automation of semantic segmentation is the most essential yet challenging task because it generally requires a large amount of time to manually segment the point clouds, and it's also an error-prone process. There are many studies in automating semantic segmentation of point clouds, which can be divided into model-driven and data-driven methods. The model-driven method classifies the points based on the predefined descriptions, such as object shapes, surfaces, or predefined criteria and seed for grouping the points. And this type of approaches usually requires prior knowledge for predefining. Another type of method is the data-driven method, which predicts points to objects using training data. Example includes future clustering-based method, which cluster the points into groups based on their similar attributes. Also, a rising trend in this type of method is a deep learning-based approach, which can learn the futures automatically. This line of research usually requires large-scale data sets for training. I would say there are no dominating type of method over another because each method will have its best suitable application scenarios. The selection of the method will depend on the data sets you're going to deal with. So let's take a look at the data sets in this challenge. There are a total of 6 training pairs. Each contains a point cloud and a 3D CAD model of a corresponding building. Here shows 3 training pairs as examples. Besides the XYZ coordinates, the point clouds have RGB and intensity information. And in the CAD model, each building contains 6 to 9 types of structural objects, which are ceilings, floors, doors, windows, columns, stairs, etc. Let's take a closer look at the point clouds. We can find that the buildings have compacted interiors that are filled with furniture such as chairs and desks. And the outside of the building, there are clutters like vegetations. There are also scanning artifacts like the floating points. These clutters are not structural objects and not presented in the CAD model, but their existence will cause occlusions to target structural objects like walls or floors. And if we register the point clouds to the CAD model, we can also identify some geometric disagreement between them. So in these figures, the colored objects are the CAD models and the gray-white objects are the superimposed point clouds. We can see that in the figure at the left side, The stair has different lenses and slopes into two files, and the point clouds show a higher wall height than the CAD model. In the upper right figure, the base of the ramp goes up from left to right in the point clouds. And in the figure at the lower right corner, the column have horizontal shifts between the point clouds and the CAD models beside of the topography differences. So based on the examination of the data sets, we can see that the complex object types in the building interiors makes it difficult to craft effective predefined descriptions or features to segment points. On the other hand, the point clouds and corresponding CAD models provides good opportunity for deep learning-based approach to learn the predictive features. However, certain challenges exist for making use of the data set. First of all, is that the deep learning models that work with point clouds, you will require label point clouds as ground truths. However, this label information is stored in the CAD model. Also, there are geometric disagreements between the CAD models and the point clouds that will cause mislabelings when you transform the labels from CAD to the point clouds. Therefore, as an extended research of our previous interest in expanding the labeled point cloud data sets in the construction domain using existing models, our objective is to generate labeled point clouds as training data sets using the given labeled CAD models and unlabeled point clouds, and then to train a deep learning model that can effectively learn the geometric and semantic features of the target objects to automatically segment point clouds. The methodology we took consists of 3 steps. To speak in a high level, the first step is to transform the label information of object classes from CAD model to the point clouds, where annotated real point clouds are augmented by synthetic point clouds. The second step is to train the deep model to learn features from produced labeled point clouds. And lastly, the segmented results of a testing model are used to generate 3D models in the BIM platforms. The first part of transforming label information from the CAD models to the point clouds is to add annotations on the real training point clouds. The real point clouds have the most close characteristics and information to real-world ground truths. To achieve this, a transformation relationship between the point cloud and the CAD model is identified first. And then the vertices coordinates of each object in the CAD model are extracted and used to crop the corresponding regions in the point clouds and assign labels to that region. And to eliminate the errors caused by the disagreement, manual check was done to modify the cropped regions. Although annotated real point clouds provide closer characteristics to the ground truth, it's still a time-consuming process. To reduce the complexity while not at the cost of losing too much accuracy, 3 steps of object classes were used in the annotation, which are the ceiling, floor, and the wall, as they consist of the most portion of the structural objects in the model. And 2 annotated point clouds were generated for model 01 and the basement of model 06. On the other hand, synthetic point clouds have proved to be effective in augmenting the real-world datasets when obtaining a large training dataset is difficult to achieve. In this task, for each building, objects of the same classes are extracted from the CAD model and used as input to a FME platform to generate synthetic point clouds. The synthetic point clouds for each object classes are then registered back to become complete point clouds. We have produced 6 synthetic point clouds for all training models, and we also include all object types in the synthetic model. Following the generation of the labeled point clouds, we made preprocessing to datasets for training, and then train the models using the labeled point clouds. I'll leave the floor to my teammate Jill for the second half of the presentation.
Thank you, Willow. So if you can go to the next page. Yeah. So for the semantic segmentation, I'll start with the pre-processing of the point cloud. So there are mandatory tasks. First, we downsample the point cloud based on spacing. So basically keep a minimum point spacing between two neighboring points. This will reduce the number of points, so improve our processing time while maintaining the level of detail. The second step is to remove the furniture, vegetation, and scanning artifact from the testing dataset. So the original point cloud captured detailed information of the scene, as we can see at the bottom left image. So we can observe some furniture here. However, these objects are not existed in the training dataset, because the training dataset we generated from the CAD model, and the CAD model only contains information of the structures. So an alternative will be to label everything in the point cloud, but they will be like unrealistic for us. So we choose to remove this furniture, vegetation, and scanning artifact in the testing dataset. The third task is to tile the point cloud into grids. An example is shown on the bottom right figures. So this is just to keep the spatial coverage of each input data set similar. Okay, the next slide. So the downsample and tiling is straightforward, and I'll talk a little bit about the furniture, vegetation, and scanning artifact removal. So we did it in two steps. The first step is we extract the ceiling and floor based on the height threshold. Okay, the next slide, please. The second step, we extract the walls based on the point density. So the assumption here is that between the ceilings and floor, areas with high planimetry point densities corresponding to the walls. So on the left figures, we show the point density map, and based on thresholding the point density, we can identify areas with high point density and then extract the points within these areas. Okay, next slide. For the semantic segmentation, our goal is to label the link the point cloud to a label, but at an object level. So for example, a wall in a point cloud can have like thousands of points, and we want all these points have the same label, the wall, instead of like 90% of the points have the label of the wall and the rest of 10% have the label of like windows. So super point graph, it fit very well with our purpose, and that is why we choose this method for semantic segmentation. The method first segment the point cloud into geometrically homogeneous partitions. So these partitions can be like planar segments, for example, walls, ceilings, and floor are planar segments, or linear segment, for example, the columns, the beams are linear segment. Next slide. And in the deep learning models, it not only uses the information from individual points, for example, the coordinates, it also uses information, some geometric features we calculate from this partition, for example, the length and width of the partition. And most importantly, it models the adjacency relationship between these partitions. Okay, next slide. Here we are showing some sample results from the semantic segmentation. So this is the point cloud colored by RGB, and this one is the label point cloud generated from the CAD model. Okay, the next two figures shows the partitions, and the next one is the prediction from the semantic segmentation. So here, by comparing the prediction with the ground truth, we can see there are some discrepancy here. And the last step will be on reconstructing the BIM models. So here from the segmented point cloud, we first extract the boundaries of the group points and calculate the corner coordinates of the walls, ceilings, and floors. And the windows and doors are identified based on detecting the openings in the walls. So these are the 5 classes we have in our result. So here we are showing the semantic segmentation result and the building information models. Okay, next slide. So the next few slides show our result on the testing data set. So this is a screenshot of the point cloud, original point cloud colored by the RGB. The next one. And this slide shows our semantic segmentation results. So first, we only use the coordinates information. We only use the coordinates information from the point cloud because RGB and intensity are not available in the synthetic point cloud. And the table shows the data set we use for training and validation. So we have 2 real point clouds and 6 synthetic point clouds. On the right, this is our training result. Here, one observation we can see here is that the accuracy varies different classes. So class with large number of points, like the walls, like the ceilings, they have better accuracy. But the class with a small number of points, like the stairs, windows, and doors, they have lower accuracy. Okay, next slide. Finally, we're showing our segmented point clouds and the final BIM models. Okay, next one. So in conclusion, we've learned a lot through this scan to BIM challenge. And currently, our model, our finding is that we are able to use the label real point cloud together with the synthetic point cloud to train our model. And in the future, we are looking into first to automate the process of generate the label point cloud. Second, for the semantic segmentation, the focus will be we'll focus on how to handling the class imbalance. And the third is for the BIM model reconstruction, how to automate this process. Okay. This is all for our presentations. Thank you very much, and we're happy to answer any questions.
Great. Thank you, Yang and Jill. That was a great presentation, and congratulations again. I see one question. There are 2 questions in the Q&A. The first one is, which FME software did you use to create the synthetic point clouds?
It's the FME software. It's a module called FME transformer. Basically, there's a FME transformer, and then there's a taker that you taking each classes of the CAD models you want to input, and then you basically combines the objects that you want to go into the same objects, and then goes into the transformer. You can output this into a uniform synthetic point clouds. Okay, and there.
Yeah, the second one is the first question is, are point clouds label ceiling floor done manually or using an algorithm? And the second question is, how are you clustering point clouds for wall and floor thickness?
Okay, are point cloud labels done manually or using an algorithm? Okay, I'll answer this one first. This is done by I will call it a semi-manual process. First, our algorithm was used to extract the vertices coordinates of each objects from the CAD models, and then we apply those vertices coordinates to the point clouds to provide real training point clouds, and then we crop the regions into different objects. And then because there are discrepancies between the CAD models and the real point clouds, to eliminate the errors, we did a manual check on those cropped regions to improve the accuracies of the results. And for the second question.
For the second question, I think, yes, the walls and floor, they have certain thickness, and in the LiDAR point cloud, it will appear to be like two planar features parallel to each other. And because our algorithm mainly segment these planar feature, linear features, so we'll get two planar segments.
Okay, great. And another question is asking, how did you remove furniture and vegetation?
Oh, that one is based on the point density. Well, if you can go to slide 16.
Mm-hmm.
Yes. So first we calculate the point density in 2D, and then we do a thresholding to identify the area with high point density. And then we extract points within this area. So in that case, like we can retain most of the walls while removing most of the furniture and vegetation.
Okay, great. All right, maybe we have time for one more question. How many synthetic point cloud did you generate, and what can you say of the diversity of the CAD models, the type of buildings?
Yeah, I'll take this question. We have generated 6 synthetic point clouds, one for each of the training buildings. As for the diversities of the CAD models, with respect to the type of the building, I would say the walls, most of the walls aligns well between the CAD models and the point clouds. However, the outside of the buildings and also for the objects such as stairs and also columns and beams, which has a relatively small area of occupation, well, they actually have larger shifts. And by generating, by casting areas, coordinates areas from the CAD model to the synthetic point clouds, this will cause large errors for those kind of objects. And that's also why we eliminate those types of objects in the annotated point clouds. I'm not sure if that answers your question, or did I go to some direction that was not your intention?
This is a question by Andre. Yeah, okay, he says this. Yeah, great, thanks. Yep. All right, thank you. There are a couple of more questions there if you can stay online, and since we need to move on to the next presentation. Thank you very much, Yang and Jill.
Thank you.
And congrats again. Thank you.